Hello, yes. Is the mic okay? Yeah, okay, great. Yes, as mentioned, today I'm going to be talking to you all about big numbers. So these are numbers that are bigger than what we can kind of naturally do in JavaScript by default. That's my Twitter handle there if you want to find me. I was pretty late to the party in terms of Twitter, so the last letter of my first name and last name are kind of collapsed, but yeah, you can find me there. Just a bit of a warning, there will be some math in this talk. It's kind of hard to talk about big numbers without talking about math, but I'll try and keep it as easy and kind of as light as I can. So firstly, numbers. You know, what are their characteristics? What are the kind of defining features about numbers? So firstly, we want to be able to store some value that then we want to retrieve at some later point, potentially print it out on a user interface. But really, the unique and defining characteristic of numbers is the ability to do operations on those numbers, these predefined mathematical things. So things like addition, subtraction, multiplication, and division. Now, JavaScript it only has one number type, and it's a 64-bit floating point number, the IEEE 754. This isn't unique to JavaScript. You'll find it in other languages like Ruby, Python, and Java. So we're not alone in having this type. Now let's have a bit deeper look at that. So this is 64 bits here. Now the first bit is what we use to control the signs. This is whether the number is positive or negative. The next 11 bits I like to think of them as the scale. So this is how big or small the number is. And then the last 52 bits control the actual value of the number. Now I've got 52 bits written there because it sort of has 53 bits in that it assumes it has 53 bits, but the first bit is always 1. So we can store 53 bits worth of information there, but we only have 52 bits. And this number system is very similar to scientific notation, if you've ever seen that, which you probably have. So you have a value, say in this case 8.12, and times by some scale to give us our result. And this is exactly how floating point numbers work as well. Now I mentioned we have 53 bits. And it's no coincidence that the max value we can store inside of these numbers is what happens when we set all of those values in the value component to 1. We get 2 to the 53 minus 1. That's our maximum value that we could store. And this also happens to be number.maxsafe integer. If you've seen that number around but you didn't know where it kind of came from, sorry, it's at the bottom of the screen. Number.maxsafe integer is what it is. If we set all of the exponent bits to 1, so the scale part, we get this huge number here, which is known as number.maxValue. But it's kind of a bit useless for what we want to do in that if you have a number, say in this case, number.maxsafe integer, and you add 1 to it, you get what you expect. But if you add 1 to that again, you're going to get something you didn't expect. It didn't do anything. And there's sort of all this weirdness when you start to go above number.maxsafe integer. So for our purposes, we're going to say that because the defining characteristic of numbers was these operations, we really don't want to be going above that number, or we're going to have unexpected consequences. So that's where JavaScript is. Now let's think about how we could go bigger, how we could push numbers to both store values much bigger than max safe integer, as well as be able to do operations on them. Now you might be asking, why? Why would I be interested or care about big numbers? And there are very valid and practical use cases for using big numbers. So say if you're dealing with big distances, say astronomical units, or you're doing any kind of accumulation of big historical data. So say you're counting the amount of characters in tweets over a period of years, you might start to run into these problems as you start just piling counts on counts on counts. Another common use case is if you're shifting decimals. So say you have a decimal value and you want to shift it to become an integer value. That shift you might kind of hit into these problems. But really it's kind of just a bit of fun. It's for us to see how far we could push this idea, how far we could overcome this limitation of JavaScript, or these 64-bit floating point numbers. And it's also a bit of a challenge for us as well. And hopefully we'll learn a lot by trying to overcome those barriers. There's actually a lot of different ways of doing big numbers. I've put a repo up there. I'll link it on Twitter as well afterwards. And this has a few other ways of doing them. And hopefully after this talk, you'll see that there are probably lots of different ways that I didn't even explore about doing big numbers. So let's get into it. This is my first technique, and this is probably the most basic, but very interesting technique, and that's converting numbers into strings. So say we have the number 125, we simply convert it to the string 125. And this is really easy to do. All we do is we take a number and we convert it to a string. This is sort of the format of that system. By doing this simple trick, how big can we go? So say we had 3 slots. The biggest value we could store in 3 slots is 999. And in a more general sense, if we had n slots, we could store 10 to the n minus 1. That's the biggest we could store if we had n slots. Which raises the question, well, how long is a string? You know, how big can these things be? And the answer is today it's actually pretty vague. It's not sort of locked down in any spec anywhere. But if you test it in browsers and in Node and things like that, you'll find that this is probably a safe value to use, 2 to the power of 27. That seems to be pretty safe and consistent. So that's what we'll be using today. But so you know, in ES7 it is hopefully going to be cleaned up. In that spec it is going to set it to 2 to the 53 minus 1, 2 to the power of 53 minus 1, which is that number.max safe integer value we saw before. But for today we're going to be using 2 to the power of 27. So we have this new max value of 10 to the n minus 1, but what is that? What does that even mean? Like how big have we gotten? Now I've come up with this analogy, which I'll be using for the rest of the talk as well. So say we had a sheet of paper, and on that sheet of paper we start writing numbers. So on the first line we write the number 1, and then 1,000 on the next line, 1,000,000 on the line after that, 1,000,000,000 and so on. And each line is a centimetre big. The thing to note is that each centimetre is 1,000 times bigger in value than the centimetre before it. So, with JavaScript numbers, we can get 6 centimetres down this page until we hit that max value, or max safe integer, sorry. If we use this string method, it would take 4,474 kilometres worth of paper to store this number, which is pretty staggering when you consider that each centimetre is 1,000 times bigger in value than the centimetre before it. So this is like a really simple technique, and we've just completely blown away that max value that we had before. And to put it in sort of terms that we can understand, it's from here in Berlin to England and back twice, with each centimetre being 1,000 times bigger than the one before it. So this is a little diagram I'm going to table I'm going to keep referring to as we go, just to kind of record our progress. So by simply switching to decimal strings, we've now got a huge increase in scale. But you might be thinking, that's great. Like, we could now store these big values, but really what we cared about with numbers is the ability to do operations. So, I think the screen's gone. Here we go, okay. So, say we wanted to do addition with 2 strings. So we have the string 256 and 182. How do we even begin to start doing addition with these numbers? Well, firstly we could look at the first column on the right. Now, we want to add 6 and 2. And we could create some system where the character 6 plus the character 2 yields the character 8 and not actually do any math. But because these are small integer values, we can probably just lean on JavaScript numbers under the hood to sort of do these small safe operations. So we'll do that for convenience. So we have the number 6 and the number 2, and we get 8. Move down to the left, and we have 5 plus 8, which gives us 13. We've got a bit of a problem because we can't store 13 in one column. So we do this sort of primary school mathematics technique where we subtract 10, carry a 1, and write the remainder in the current column. So now we write a 3, and we carry that 1 over to the next column, and then we move down, and we have 1 plus 2 plus 1, which gives us 4. And we were able to add these strings, which was pretty fun. And what's interesting is that was actually kind of a really nice algorithm. We were just looking at 2 numbers at a time, and we were just constantly shifting down the number. All right, let's take a look at subtraction. This one's a little bit harder. So say we have the number 4,005, and we want to subtract 11 from it. So we have 5 minus 1, which gives us 4. Then we kind of get into this weird situation where we want to have 0 minus 1. We can't really do that. So we start what I like to call is like a lookup phase. So we start looking down the number until we find something that we can borrow something from. So in this case, we found 4. We take 1 from that. We can carry a 10 back. All right, now we can take something from that. So that becomes a 9. And we carry the 1 over. And now we can do something. We can take 1 from 10, which gives us 9. Okay. Then shifting down again, we have 9 minus 0, which gives us 9, and 3 minus 0, which gives us 3. Okay, and we got our answer. But that was kind of gross, right? We started shifting down, and then we did this search, and then we had to come back, and we had to search again. And if these were really big numbers, this could be extremely inefficient. You might be searching back and forth a lot. So that's something I just want to keep. This was much different to what we had with addition, where we were simply moving down 2 digits at a time. So that's just something to keep in your mind, that that's sort of a pain point for this system. Now let's look at multiplication. Bear with me, there's not too much heavy math more to go. Okay, so multiplication. We could write a multiplication algorithm, but really, once you have addition, you can deduce multiplication for free. So you can think of multiplication as just doing addition in a loop. So we start with 0, we add 10, we add 10, we add 10, and we're done. We have our answer. And what's cool about that is we didn't need any kind of new math. We could just leverage that addition function we already had. Admittedly, it's not going to be super performant, but that doesn't really matter for now. Okay, division. Same kind of idea, except now we're just going to keep looping. We're going to keep subtracting from this number until we can't subtract anymore. So say we start with the number 6, we subtract 2, we subtract 2, we subtract 2, and we can't subtract anymore. And what we do is we just count the amount of times that we could subtract. And we can count because we had that add function that we created before, and so the answer is 3. And so by having addition and subtraction, we were able to get division and multiplication for free, which is pretty great. So as soon as we create a system with addition and subtraction, we can create one that has division and multiplication as well. So we did pretty well. We created a system which has a huge new value, as well as being able to do these predefined mathematical operations. And the really cool thing is I actually built this system. So again, I'll tweak this at the end. If you're interested, you can kind of have a play with it. And it works for decimals as well. I didn't go into those, and negative and positive values. But yeah, it actually works, is the thing I want you to take away from that. I wrote here on my slide notes, do not use in production. I haven't really tested the performance or anything like that on it, but it's just sort of interesting if you want to have a look at that. So I'm now going to move to the next technique, which is binary strings. So this is the binary representation of the number 118. It's an 8-bit representation. Now the max value in this system is 2 to the n minus 1 minus 1, and with n being 2 to the power 27. And why it's minus 1 is because I'm storing the binary in a format called 2's complement. And I'll explain why that's important in a sec. So now we've got a kind of bigger value than what we started with numbers, but a smaller value than our base 10 system. And that's because we're now in a base 2 system, like each digit we can't store as much information in there. But it's still 1,347 kilometers on this sheet of worth of paper, with every centimeter being 1,000 times bigger. So it's still a very big number. But let's take a look at subtraction in this system. So we have the number 5 and the minus the number 3 in binary, and we know that this is going to give us 2. And we can use this method called the 2's complement to sort of model this in a different way. So firstly what we do is we flip the bits and we add 1, and then we can simply just add. We can just add like we would before. So in binary addition, 1 plus 1, you carry the 1 and you leave a 0. So we go over, now we have 1 in this column. We have this carry situation again, 1 plus 1, so we have 0 and we carry the 1. Now we have 1 plus 1 again, so we put 0, but we're carrying a 1 kind of into this area that we don't care about. This is called the overflow bit. And in this system, you just throw that bit away, you don't care about it. And what's interesting for those who kind of know binary is that we've ended up with the number 2. So even though we had this subtraction problem, we were able to model it using addition. So we started with a subtraction, we flipped the bits. Oh, you can see the animation, but I can't. And so we actually ended up looking at it like this. We've been able to model subtraction as if we were doing addition, which is really nice. It's a really nice kind of way of looking at the problem. But let's go bigger. We've looked at binary strings. Where can we go from here? Well, let's have a look at hexadecimal strings. So hexadecimal strings, hexadecimal, this is a representation of the number 126 in hexadecimal. And hex is really simple. It's just a mapping of 0 through 9 is 0 through 9, and A through F is 10 through 15. So you can store 16 possible values in each string, each slot of a string. And so now we have this new max value of 16 to the n minus 1, which is bigger than what we had in decimal. But it's going to have probably a bad subtraction story. But we're moving now in the direction of trying to chase bigger and bigger numbers. So this one's now 5,387 kilometers worth of paper. But what I wanted to have a look at with hexadecimal is, we said we could store 16 possible values in each slot of a string, which kind of leads to the question, what can we store in a slot of a string? What's the maximum thing we could store in there? Which leads me to my final technique for strings, which is 16-bit strings. And to understand this technique, we need to understand how strings work a little bit better. And to understand strings, we need to understand Unicode. So Unicode is really simple. It's just a map of symbol to integers, or symbols to code points. And that's all it is. So code points, they just decided arbitrarily that these symbols map to these integers. That's all it is. And there's about 1.1 million of them. Now, JavaScript as a language has decided that it's going to treat every 16-bit unit of a string as one character. And I'm going to show you what that means. So let's start with this string here, the letter E. It equates to the Unicode integer of 101. Now, you can pull that out from the string using code point at, and it's going to give you that integer back. But you'll see it's in hexadecimal and in the Unicode kind of string sense, it equals /U0065 and has a length of 1. And this will be true for any character that has a Unicode code point between 0 and 2 to the power of 16. Things get interesting when we start to move to characters that are bigger than 2 to the power of 16 in integer value. So in this case, we have an emoji, which equates to a code point. And you'll see that it actually equals, in JavaScript, it's 2 different Unicode strings and has a length of 2. So even though visually to us it seems like it's 1 character, according to JavaScript as a language that we deal with, it's 2. And this gets even more crazy when you start to introduce things like modifiers, where according to Unicode it's 2 huge numbers, but JavaScript needed 4 16-bit strings to represent that. So even though it looks to us like 1 character, JavaScript's calling it 4. So really the biggest things that we could store inside one slot of a string is anything from 0 to 2 to the power of 16. So we have 2 to the power of 16 possible different things that we could store in each of these slots. Which, to put into perspective, if we looked at the piece of paper in terms of kilometers, it's with each centimeter being 1,000 times bigger than the centimeter before it, it would be from here back to my hometown in Sydney and a little bit back again, or around 21,000 kilometers. Was how much paper we would need to record that value. But what about operations? If we had the string hash plus $, what does that give us? Well, we saw this method before where we could pull out the integer value. So we can just simply pull that integer value out, do the addition, and if we really wanted to, we could actually save that result back into a Unicode string. So if you didn't know, hash plus $ equals capital G. Cool. So we've got a pretty big increase in scale. It's kind of pushed us to the limit of what we could do with strings. So where do we go from here? Well, let's have a look at arrays. So firstly, we had a string, and I've been very deliberate with my language in saying that a string has slots. Now, we can also think of an array of characters. So we can think of a string as an array of characters, but we also have arrays in JavaScript. So technically, we could store anything we want in one of these slots. We don't have to store just 1 character. And then the kind of conclusion of that is we could store one of these superstrings that we created in each slot of an array. So how long is an array? Well, an array is 2 to the 32 minus 1, just so you know, which means our new max value is this huge thing here. To put into perspective how much paper we'd need to store that number, you would have to go from the sun to Pluto. I like mentioning Pluto because it was a planet when I was young, and I don't know, I like keeping it relevant. So from here to Pluto, from the sun, to Pluto, 135 times. That's how much paper you would need. So yeah, it's about 3 trillion kilometers worth of paper, with each centimeter being 1,000 times bigger than the centimeter before it. So these numbers are just like, I can't even process them. And this was just one level deep arrays, right? We're just looking at an array that has strings. There's nothing stopping us from having arrays of arrays or arrays of arrays of arrays. And the numbers start to get absurd, and I couldn't even really think of any good analogies for them anymore. Now, something you might have been thinking about this whole time, and definitely with the arrays, is memory, right? Can we actually store these things? So let's have a look. We start with this string. We know we have 16 bits per slot. Now, they might do some optimization under the hood, but let's assume that it's 16 bits per slot. We have 2 to the 27 slots. And the amount of bits is about 2 billion bits, or 268 megabytes, to store one of these strings. And if we're trying to store an array, we have 268 megabytes per slot, 2 to the 32 slots, about 1 million terabytes to store one of these things. So definitely something that you don't want to be doing. All right? So we're going to stick with this. 268 megabytes is kind of something we can probably deal with. Now what we could do is if we were running in Node, by default you get about 1.7 gigabytes on a 64-bit machine. You could increase the amount of memory your Node process has to kind of work with these things more naturally, but if we're starting to do this, we're probably going down an approach that we shouldn't be going down. So let's take a step back. Let's think about what we've learned from looking at this string approach to doing math. Firstly, we learned that if we can do almost any operation if we can add. If we're using a binary system, if we can add, we can kind of do lots of different operations. And we can add numbers together, potentially really big numbers. We only need to look at 2 digits of that number at a time. So just kind of looking down the columns, shifting to the left, sorry. Okay, so let's take those learnings and apply them somewhere else. So say we have this file, and it's encoded in UTF-8, which means you have 8 bits. It's a flexible 8-bit encoding. Okay, now in this file we have a binary string. And it's huge, it's like 10 gigabytes big, much bigger than we could store in memory at once. And let's say we have 2 of those files, sorry. We could open a stream to those files. This is sort of like a live connection to the file without reading anything in. And then we create a buffer where we're just going to read in 1 byte at a time from each of these files. And this is why it was important that it was UTF-8, because 0 and 1 fall in the first 8 bits. We'll be able to read in 1 digit at a time, which is what we wanted to do. We just want to read in 1 digit at a time from these files. So we read in 1 digit at a time, we do the operation, we might save the overflow if there is one in memory for a little bit, and then we output that 1 byte at a time to an output file. And this is pretty cool. This means we could actually add incredibly big numbers that we could never really store in memory by just looking at 2 little things at a time and just adding them and kind of passing it on. I actually built this one as well. This is in the repo if you want to check that out. And we can think of it like this. So you have 2 input streams. So you get 2 digits, say a 1 and a 0. You add them, you get 1, and then you save it to the output file, and you just kind of keep doing that process. And it's very similar to what we had before, where we just keep shifting down. We can do this on numbers that are much bigger than we can store in memory. So now this table starts to break down, right? Our limiting factor is not, I'm sorry, I know you probably can't see the bottom of the screen right now, but I've just written infinite, right? Your limiting factor is how much memory you have on your machine, which is a pretty big increase in scale, right? I didn't even bother to figure out how big in terms of kilometers that would be. But we could take this further, right? We've limited by our own machine. Well, what if we weren't even limited by our own machine? What if we instead distributed this number across multiple machines? So no one machine could ever see the whole number at once, but all these different machines had pieces of the number. We could store them using that, and we could also create some sort of protocol to do distributed operations. Because we don't actually need to see the whole piece of the number at once to do an operation, you only need to see 2 digits, we could distribute how we do this addition across multiple nodes, and then stream that output to someone who cares about it. Right? So now our limiting factor isn't even our own machine, it's how many machines we have access to. All right. So we went big. We went really big. We probably went bigger than you thought we were going to go today. Limiting factor being the amount of machines that you have. And we actually learnt a lot from implementing a number system using strings, which you might have thought was a bit strange to start with. And we were able to take those learnings, some of the kind of nicer patterns that we found about dealing with strings, and we were able to apply that in a completely different way to build a number system that maybe we didn't think about when we first started. And so my big takeaway from today is, don't be afraid to try something a little bit different. You might actually get some learnings from that you can apply to some other problem, or to find some solution that you didn't even think about when you first started. Yeah, so you never know what you'll learn and where it will lead you. Before I finish, just want to acknowledge a good mate of mine, Stephen Campaign. He's a math teacher, really helped me out with a lot of the heavier math in this talk, so big shout out to him. And also all my amazing colleagues at Atlassian whose ear I've been chewing off for the last few months, wrapping my head around some of these problems. If you do want to use big numbers in production, there is a library, you can kind of use that. Also, if you are interested, they're looking at putting infinite precision integers into JavaScript. There's a stage 2 proposal kind of on GitHub. You can check that out. Great. Thanks, everyone.